If we have data that is normally distributed, then there are two types of tests that we need to decide which one we're going to follow. There's a z-test and a t-test. Now the z-test is for when we know the population standard deviation, which is known as sigma. And the t-test is for when we don't have that, but we do have a sample, and either we've been given the standard deviation for the sample or we can work it out. And the sample standard deviation takes the letter S. So whenever you're reading a question to decide whether you're going to follow the z-test on the calculator or the t-test, you need to look whether you've got a population standard deviation or a sample standard deviation. You won't have to swap between the two. So in this first example, we've got a machine filling flour with a labelled weight, so that's going to be our mean. To make sure they're being filled correctly, we take a small sample and we find the mean of the sample. So we're going to see whether that is statistically different from the mean they're claiming. But from past experience, it's known the standard deviation of the bags filled by the machine is 20. So that's our population standard deviation, so sigma. So we know sigma, and therefore we're going to do a z-test. So on our calculators, we go to Stat, Tests, and number 1, z-test. And for this example, we've got the stats rather than the raw data. We haven't got a list of all the values for the bags, so we're going to choose stats on the calculator, and then we're asked for various pieces of information. So mu naught, what's the mean we started with, is 1,000 grams. Then asks us for sigma, and we've already established that we know sigma in this case is 20. X bar is the mean of the sample, and that's in the question, is 995. And N is the number of items in the sample, which in this case is 40. Then we've got to decide what our null and alternate hypothesis is. So obviously our null hypothesis is that the mean is 1,000. Our alternate hypothesis is the bag filling to less than the correct weight. So is mu actually less than 1,000? So on our calculator, where it says mu colon, we're going to choose less than mu naught and highlight that. Then click calculate, and we get a Z value of negative 1.5811, a P value of 0.05692, X bar and N, which is the stuff we input anyway. Of those four values, the P value is the important one, and we're going to compare that against our significance level. So how does that compare with our significance of 0.05? Well, it's slightly larger than 0.05, which means we can't reject our H naught. So it's not good enough for us to say that the mean isn't 1 kilo. We could have got this sample just by chance and the mean still being 1 kilo. So the mean really is 1 kilogram. To find the critical region is very similar. It's again, the calculator can do it for us. It's under stats and tests, and it's number 7, Z interval. and you'll find that it's already transferred the data across from the first part of the question. So it's told us that sigma is 20, x bar is 995, and n is 40. We just need to put in the confidence level. Now this is where we have to do a little bit of thinking, because we want 5% to be less than. So I want 5% to be less than my value. Now the calculator can only give us a confidence interval between two symmetric points. So we imagine that we have a symmetric point at the top end of 5%, which means that in the middle we've got 90% of the data. And that's the value we're going to use as our confidence level, 0.9. Because we've got a one-tailed test, not a two-tailed test. And if we input all that information and hit calculate, it gives us the range of 989.8 to 1000.2. Which means that for our critical region in this case, x would need to be less than the lower value, 989.8. So if our sample of 40 items had a mean of 989.8, then we could have rejected H0, but actually it was 995, which is quite a long way above that, so we can't reject H0.